Right. So typically we know that work is equal to a change in kinetic energy. And so we're going to find out this, something new, talk about this new quantity called potential energy of a system. Oh, that's what I was going to say. But systems typically are made up of two or more objects. I like to think of them like that because in the context of potential energy and change in potential energy, we're always dealing with two or more objects. I think the whole one object system, it's if you're talking about one, like for example, when you're doing a free body diagram on a book on a table, well, the book could be the system and everything on the outside and all contact forces and field forces, like the force of gravity, would be outside of that system, which is the book, which is the object of interest. So, but systems typically, conventionally, are in terms of two or more objects. Okay. Should be at 7.6. So always read the sections, read through all the examples, just get as much understanding as you can, and all of that. But what I like to do is just to take the sections and make them as simple as possible. Okay, so 7.6 potential energy of a system. We've seen already that the network in the system is equal to net force times the displacement. Without a displacement, you have no work. Without a force, you have no work. So you have to have both of those together to have network by some force. And we also derived last time that when a net force or some force does work on an object over a displacement delta x, you have changed its kinetic energy. So in essence, network in the system is equal to change in kinetic energy, which is known as the work energy theorem that we talked about last time. And we did problem number 29 and some other problems to show that, to apply this. So the network in a system is the change of kinetic energy. So next, I want to now return to our system of a ball and the Earth, the ball Earth system that we were talking about at the beginning of this chapter, when we were talking about how systems are typically two or more objects. Let's say that we have this system of the ground and we have the ball on the ground. And this circle represents closing the system off from the environment, from the rest of the environment, from air resistance, from anything else, any outside forces. So the system is just those two guys here. The ball Earth system. So the ball is on the ground, and I'm going to ask you how much work is done by the Earth on the ball. You can shout that out. We're all friends here. We don't have to. That's squeamish. Anybody? How much work is done by Earth on the ball in this system? Is it zero or non-zero?
Is it zero because it's stationary?
Yes. There's no displacement, so therefore there's no work. We always have to remember our definitions. These are key. These are not just writing down and you take notes and get about it and then you go to problems like, this is important. The relationships are very important. There is no work because there's no displacement, therefore there's no movement, stationary, nothing's happening. There's no work done by the Earth on the ball or the ball on the Earth. This is a situation, this is another explanation of Newton's first law in terms of work. The net work is zero, the net force is zero, object at rest stays at rest. So there is no work. Zero work done. Either case. So, okay. Now let me raise the ball in the air. So now my system looks like this. Earth down here, ball up there, chilling out. Okay, stationary. I just raised it up, so like you raise an object in the air, keep it there. Velocity at top zero. There's many things we can talk about here. All right. Force of gravity towards the Earth like that, but I've raised it up to a height, delta y or delta h, whatever. Let's say that the ground is my initial position because I'm going from ground to someplace in the air. This is not negative, so it's just arrow, I guess. You get the idea. From initial position, y initial to the ground, from the ground to y final in the air. Ball is stationary. Another question coming up. Somebody besides Emmanuel. Spread the joy around. So it's stationary, but the force is still there. Have negative Fg pointing down. It's always on point down towards the center of the Earth. The center of the curvature of space-time. And delta y is positive. You raise the ball up in the air. How much work this time? Okay. How much work is done by the Earth on the ball? Hey, work is force times displacement.
Is the ball stationary in the air or is it falling?
Stationary.
Okay.
How much work is done by the Earth on ball? So yeah, I mean, nothing's happening besides it's stationary. Is it zero work or non-zero? No, work is force times displacement. We have a force, we have a displacement. How much work is done by the ball then? I mean, by the Earth on the ball?
Zero because it's stationary, right?
Perfect. That's right. Don't be fooled by that. There is no work done because of the definition of, even though we have this, there's no change in kinetic energy. There's no change in the displacement because it's stationary. Therefore, the work is still zero. So conundrum, maybe. We know that work is force times displacement. There's definitely a force, there's definitely a displacement. So why is there no work? What's happening here? Next thing. There is 0 work done by the Earth because of 2 reasons. There is no displacement, as Lily told us. As the ball is in the air, it's just stationary. There's no displacement once it's there hanging. There is no displacement. Delta Y. And there is no, by default, there is no change in kinetic energy or no work. You always know if something, if a force is going to do some work, if it moves, something's moving. Ball stationary, 0 work. I'm just approaching this idea in 7.6, different point of view. Okay, but since there is an FG, there's a force due to gravity, obviously, it's always going to be there. And a displacement. These things exist. There is a force due to gravity. There is a displacement between the stationary ball and the Earth. There's some space. There's some height, or delta Y. Oops. Since these exist, there is the potential to change energy. Why is that? Because we have a force that exists that can change the position of that ball. We drop it. Okay, that energy or that potential to change the kinetic energy actually becomes a change of kinetic energy by the work done by the force of gravity and moving it from its height to the ground. But right now, as a stationary, nothing is happening. It's just a potential. It's the ability to make this happen. Does that make sense? You have the ability, you have the potential to go far. You have to activate. There's the potential to change kinetic energy. We call that potential change the kinetic energy. We call that the change in potential energy. Because since we, by default, have stated that there is a potential to change the kinetic energy, that potential we call change in potential energy. We call the potential to change the kinetic energy the change in potential energy. We will see why even further in a moment. But this is the definition I'm going to give to you right now, the stipulation. So we call that potential the change of kinetic energy, the change in potential energy, or delta PE, like kinetic energy is delta KE, potential energy is going to be PE or delta PE in this case. Because any change in something is A difference, B difference between 2 points. Delta X, delta PE, delta KE, delta force, delta magnetic field. It's final minus initial. We have the potential to go from the top where the ball is stationary to the ground. Stationary, it was 2 different points, 2 different positions. From its initial height in the air, final height at the ground. Okay, so let's go back to this diagram. Ball stationary. Earth. We have this final point, this initial point. That's why I just keep that figure in mind for us. We have negative FG delta Y. Now, potential energy and change in potential energy obviously are not the same thing. It's like kinetic energy and change in kinetic energy are not the same thing. If you just have kinetic energy, the object's moving at a constant speed, okay, moving along, rolling along, 1/2 mv squared, 1/2 mv squared. But a change in kinetic energy is the difference between 2 velocities. Therefore, likewise, change in potential energy is the difference between 2 points. So potential energy is a function of position, similar to kinetic energy is a function of velocity. I like to call even further, potential energy is energy of position. So I can have potential energy at this final point here, as long as I have achieved a height, which I have done from going from the initial position here to a final position. The potential energy does exist at this point because I have an actual Y final. I have an actual height at this point. So therefore, you change the potential energy, you change the position. They work hand in hand. Potential energy is a function of its position or its height. We'll see that in equation form. E, potential energy, you have changed the position. Understand? Savvy? That makes sense. You see that? Do you get with that? Any questions? It's all definitions. We build the definitions, we build the tools so that we can do problems efficiently. We have to have those tools. Because then you'll be asking, what equation do we use? What was that? What's the situation? You have to know the definitions. These are important. These concepts are important. Okay, I take silence is good. Okay, have questions later? So we have stated potential energy is a function of position. The equation for potential energy EE equals force of gravity, which we'll just call mg, times height, or y. Typically just call h because we raised the object into the air, and then we can let it fall at some other time. We can let it drop. But potential energy is mass times gravity times height. If there is no height, there is no potential energy at that point. So let's look at the potential energy at the ground, which is the initial position. It's at the ground. How much potential energy would this be equal to? H or Y initial or H initial?
Nothing, because there's the initial 0.
Right. There is no height at the ground. So 0 potential energy, and all forms of energy, kinetic, work, potential energy, those all measured in joules. So there's no potential energy, or we can say 0p or 0 joules at Y initial or H initial. So now the potential energy at B, or the final point, is going to be non-zero. So when we raise an object into the air, we have increased the potential energy of that system. Got it? You raise objects up. You increase, because final is greater than the initial. So it's an increase, positive. I raise the object in the air. Even though Fg and delta y is there, I've increased the potential energy, even though there's no work being done at that moment. Okay. At these moments, it's 0 here, at the moment of Hi being 0, and H final non-zero, there's a non-zero potential energy. Increase potential energy. Or we can also say that we take the change, final minus initial, right? That makes sense. So when we raise the object into the air, the force that I do in raising the object into the air is going to be positive. Delta y is this way. I raise my hand in the air, force of hand on ball, they're in the same direction. The change in potential energy is positive. The work that I do is positive, because my force and the displacement in the same direction. But also, we know at the same time as I'm raising the object into the air, the force of my hand, the force of gravity is going to be doing negative work at the same time, because it's going opposite the displacement by the first principles we learned about work. When the force and displacement are working together in parallel with each other, the work is positive. When there's a force that is opposite the displacement, that work is negative. So now with that being said, when the object falls down, the work done by the force of gravity, or the work done by gravity, is going to be equal to a decrease in potential energy. So again, so let's continue with this stuff. If I raise object into the air, work done my hand, your hand, is positive, and there's an increase in potential. Now, let's say the ball is, it's ball, we drop it. Force due to gravity, that way, work done by gravity and the force of gravity and the displacement going to be in the same direction. We're going from a high potential to a low potential. So even though the work is positive by the force of gravity, that amounts to a negative change of potential. We've changed our perspective. Now this will become a y final, and this will become y initial, because now we're changing perspective. We're not raising it into the air, we're letting it drop. Now this becomes y initial. Let it go. Y final. This is 0. This is non-zero. So even though the work is positive, that work is equal to a negative change in potential, because 0 minus 5 is going to be a negative number. Got it? So the work done by gravity, in this case that's the force here, going to be equal to a negative change in potential energy. Or since we are talking about this gravitational force in most of our problems here, and we will be discussing that the gravitational force is a conservative force, meaning that the work that's going to be done in this system, if I raise the ball up into the air or let it fall, the net amount of work is going to be 0. And the reason for that is because the displacement doesn't change, whether I raise it into the air or let it drop. It's going to rise the same distance as it falls. So the total work in the system in that case will be 0. I go 2 joules up and I come 2 joules down. If we're just talking about gravity, right? It'll be negative 2 joules up because force of gravity will be opposite the displacement, and then 2 joules down. Negative 2 plus 2 is 0. So the work done by the gravitational force is a conservative force because there's no change in the work, in the amount of work. The net work will always be 0. But friction doesn't work that way. We'll see when we talk about conservative and non-conservative forces. Friction is always going to take energy away of the system. You can never recover the energy of that's done by friction. So with this new equation here, we're talking about the work done by gravity. We can just generalize it and say that the total work in this system, which, and the force in question here is the force of gravity, that total work is going to be equal to a negative change in potential energy. Now go back to the first principles where we talked about, right. In terms of like an object rolling on the ground, the network is equal to a change in kinetic energy. So we have another principle in terms of the y-axis where the network is equal to a negative change in potential energy down here. So when we put these two guys together, network is equal to negative change in potential energy, which is equal to delta KE. In all instances, if the displacement on the x-axis going to the right, like if we roll an object or push an object to the right, a certain displacement, and then we come back the same displacement, the total work in that system is going to be equal to 0. Just like if we raise an object into the air here and then let it fall, the displacement will always be the same. The total amount of work done in the system will be negative. All right, sorry, will be equal to 0. And that 0 work is equal, in this case, is equal to a negative change in potential energy. Any questions before we go further?
Mr. Kelly, could you explain one more time the relationship between potential and kinetic?
Sure.
Sorry, could you hear me?
Yeah. Okay, so we know that, last time we derived this relationship that the total work in the system is equal to change in kinetic energy. This is like an object on the ground going left or right. It's horizontal displacement, and we can also say vertical as well. This is what we knew from last time. Network, change in kinetic energy. We derived this equation, which is also equal to net force times displacement. We then go to this new system. I raise the ball into the air. I increase the potential energy when I raise objects up. So that was a stipulation. Raising objects in the air, increase the potential energy, or the change in the potential energy is positive when objects go up relative to gravity. Because if we're just talking about gravity in question here, which is the case when we have an object in the air, the main force in question is the force of gravity, whether we raise the object up or not. So if we raise the object up, the work done by gravity is going to be negative, because the distance that I raise it up is going to be opposite the force of gravity. And then when it falls, the force of gravity will be in the same direction as the displacement. So the work done by gravity here will be positive, but the change in potential energy will be negative. So it's like vice versa. When I raise the object into the air, the work done by gravity is negative, but that's also equal to an increase in the potential energy. And we're going to call this a special type of potential energy called gravitational potential energy, because the force in question is the gravitational force. So we call that, generally speaking, the gravitational potential energy. So this is when I raise the object up. You see that? Do you understand this part? The force of gravity, when I raise it up, will be pointing down. I see in the first picture, my displacement is going up. They're opposite. So the work done by gravity is negative, but that's equal to an increase in the gravitational potential. I've increased the energy. I've gone from 0 to non-zero. So final, let's say I go up 5 meters. 5 minus 0 is positive 5. In positive energy. But conversely, if I let the object fall, the work done by gravity is positive, but that's equal to a negative change in potential. So now I'm going from initial value of, say, 5 to 0. 0 minus 5 is negative. So since the only force in question here is the gravitational force, which in this system, that's all that really exists, we can call the total work in this system the net work, because it's only one force. So just keep it simple. So the net work in the system is equal to a negative change in potential. And we also know from up top, that's also equal to a change in kinetic. Negative PE is equal to delta KE. Or better yet, when this guy falls down, I'm increasing its speed from 0 to non-zero. So I'm increasing the kinetic energy. I'm going from 0 velocity to 5 meters per second, whatever. At the same time, I'm losing potential. You see that? Does anybody not see that? I let an object fall, I'm losing position, AKA I'm losing potential energy. But at the same time as that object falls down, I'm increasing its speed. Therefore, this guy is positive. An opposite case. When I raise the object into the air, I increase potential. Let me just make a stipulation here. This is falling down. And over here, gravitational. We're going to see why soon, another day, why there's a distinction, what the reason for this distinction. When I raise the object into the air, I increase gravitational potential energy and I lose kinetic energy. Because when it gets to its final point in the air, it's not moving. I'm going from a large value in kinetic energy, I'm raising, and all of a sudden I stop. So I'm going from, at the top, it's going to be zero velocity. That goes back to one-dimensional kinematics. Zero velocity minus some other velocity, that's going to be a negative change. 0 minus 5, 0 minus 10, 0 minus anything is negative. So this is rising in the air. That's why they're equal. This is the equality of the two. We've established this already from the previous class. Today, we've now established this relationship. Since they're both net work, we can set them equal. Questions? It's highly important that you feel this, you understand this. Silence means you understand, or questions. Now let's take this top equation again. So I'm just gonna draw this. So network equals negative change in gravitational potential energy, or network done by the force of gravity is the negative of potential energy. And do you see that?
Yeah, it's clear now.
All right, all right. This work is this is necessary. And who is it not clear to? Because make that, definitely want to make that clear. Anybody has any doubts? Get to the top, increase the potential. I've gone from 0 height, 5 meters. This is positive, this is negative. Speed at the top is 0 from some non-zero speed. They switch. That being said, network is equal to this. It's also equal to changing potential energy. We can set these guys equal to each other. We know what the fundamental equations are. Oops. Now let's do something. We know that potential energy is mgh. And you change is final minus initial. So it's going to be mgh final minus mgh initial equals 1/2 mv final squared minus vi squared. Why is that? Because we know that kinetic energy is 1/2 mv squared. You probably see where this is going. I'm going to put the like terms with each other. So this becomes negative MGH final plus MGH initial 1/2 MV final squared minus 1/2 MV initial squared. Put the initial and final terms together, guess what you have? So I'll put the initials on the left, this is the beginning. 1/2 MVI squared plus GH initial equals plus MGH final. What do you think that is? What's that saying? These are initial.
There was no change.
No change in what?
Potential energy.
Yep. Well, there's no change in any energy actually, because we have both terms. We have an initial kinetic energy here. We have an initial potential energy, final kinetic energy, and we have the final potential. This is, oh, and by definition, this is kind of leading in definition-wise into chapter 8. The sum of kinetic and potential energy of a system is known as the mechanical energy or total energy of a system. So this would be known as total energy initial equals total energy final. What this states that the energy that you have in the beginning of a system will be the same energy at the end. This is known as the conservation of mechanical energy. Mechanical because it's in terms of mechanics. Initial energy equals final energy, also known as conservation of energy, but specifically conservation of mechanical energy. So we're coming from the idiom of mechanics. And we only get there once we have derived this relationship, which is equal to the network in a gravitational field. The gravitational field is a conservative field. That means that the work done in that field will never change. Therefore, these two guys are equal. Equal and opposite forces, equal and opposite types of energy. There's energy measured in joules, but there are different types. If you lose potential energy, you gain kinetic energy. If you lose kinetic energy, you gain potential energy. The total energy of the system does not change. The amount does not change, but the types change. You go from one form to another. Solid, liquid, gas, it's still water, just different states. Close the system off, you won't evaporate any of the water. Same idea here. It's a system of conservation. And that allows us to get to this final point. All right, let's go back to the ball Earth system. And let's put some numbers. So let's say, this is my, initial height, final height, because I'm gonna drop this ball. Let's say the mass is 2 kilograms. Let's see. Say the initial height. 10 meters. Let it fall. Final speed is 0. I want you right now, use the conservation of energy Determine the speed at the bottom. Tell me what you notice about the final equation that allows you to get the final speed. HF is equal to 0. Got that there. Why don't you do that right now? Tell me what you get. Okay. Maybe there's a question here. Now, the initial energy in the system is made up of both types or one type? What kind of energy is at the top here? Is it potential energy or kinetic energy? Before it falls.
Potential.
Yeah. Because remember, potential energy is the energy of position. Kinetic energy is the energy of motion, velocity. So you accurately, that's correct, Emmanuel. So you can wipe out the KE term here. Makes life easy. So now you have all of the energy in the beginning is held as potential, and therefore all the energy in the end will be both or one type. When it hits the ground, what kind of energy will it have here? Final height is 0. Is there no energy at the bottom?
Should I say it or?
Yeah, I'm asking.
Okay, it starts off with potential and then it ends off with kinetic because the final potential energy has height, or no, wait, no. Yeah, wait,
Okay.
I think.
Yeah.
Yeah, no, the final potential energy has height and the final height is 0. So it'll wipe out potential energy for final.
Right. So we're going from initial potential to final kinetic. That's all we have. Now there's going to be some problems where we have both and mess around, but yeah. Perfect. So now let's take the equation. Our conservation of energy. So there's no kinetic at the beginning, and then there's no potential at the end. So EI equals AE final. Okay, so then we have MGHI equals 1/2 MV final squared. Look, the masses cancel out. Then we have GHI divided by 2 GHI. Yeah, actually, let me get rid of this guy. So 2 GHI VF squared VF is equal to 2 GHI. You know, gravity is always going to be 9.8, all that. So let's do this over here. Hey, mute that mic, somebody.
Sorry.
No problem. So 2 times 9.8 times the initial height of 10. Does this look familiar? This whole thing should look familiar. This equation is VF's equation.
Oh, it's when there is no initial velocity.
Yeah, it looks like a kinematics equation. So here's the beauty of conservation of energy. You can belay a lot of the kinematics. You're going to come back to the kinematics because the overarching theme here is a constant acceleration, and the constant acceleration here is gravity. So energy approach kind of makes things easier. You get back to your basics here, like indirectly, but the approach is different. Hopefully easier. You had a question, Sin?
If we got the kinematic equation, it means the energies are independent from mass,
Absolutely.
right?
Absolutely. I can put a 2-ton truck at that height. I'm just going to have the same speed at the bottom. Yeah. And also, what does that say about gravity with its respect to mass?
It's same for all masses.
Yeah. No respect of persons. No respect of mass. So feather, 2-ton truck, ball, they're all going to have the same speed. Now, even though the feather takes a longer time, it's going to hit that ground at that V final. Again, in this stipulation here, this conservation of energy means that we are wiping out friction air resistance, because for the most part, it's negligible. This becomes 14 meters per second. It's kinematics wrapped in the form of energy conservation. So that's a little bit of chapter 8. And put all that stuff together. The title of chapter 8 is Conservation of Energy. So let's get back at this again. So the total work done by, there's a section 7.7 talks about the conservative force of gravity and the non-conservative force of friction. Gravity is a conservative force, as I stated earlier, because the amount of work done in a gravitational field will come out to be 0. Friction, it will always be negative. You're always going to lose, which is why an object at a high rate of speed under the power of friction is going to eventually come to a stop, because it's losing energy every second. Losing speed, losing energy. When we put all this together, and the work net here is in the context of gravity, we can then say change in PE plus change in KE. This net work here becomes 0, because the total work done in a gravitational field total is 0. You raise the ball in the air, a displacement, you're going to drop at the same displacement. The work is the same. Equal and opposite makes 0. So this 0 is equal to delta PE plus delta KE. This is another way of stating the conservation of energy. There's no change in the work. Okay, so this is the form of conservation of energy. Now, when we put friction in there, which is a non-conservative force, friction is always not going to save anything. It's always going to take away. So things get a little different with friction. So I should net in gravity. I should no, it's the same. So I'll write it. Work done by the gravitational field is going to be 0. I have a short video that this professor demonstrates that real quick. So I want to show that as opposed to just kind of writing it. It's a nice little video. But okay, so there's that. See, friction comes in there in the mix, and friction is a non-conservative force. It takes away everything. Seen a little bit of that already. You know, we need it, you know, but you don't use friction in talking about conservation of something. Your standard physics books will always ignore friction because it's just out of context. In AP, need it, and talk about it. So the energy equation takes a different form. So the work done by friction is going to be equal to change in gravitational potential and kinetic. So this work is not zero. It's going to be equal to the work done by friction, and friction force generally is going to be the kinetic friction. So we're going to say the kinetic friction formula is going to be force of friction times delta x equals to this. Tracking so far, it's no longer zero because friction takes away. It's always going to be negative. I'm losing, losing, losing. I'll never get it back, so I can never net zero. Overall, in the entropy of the universe, it's zero, but in terms of this mechanical energy, friction takes away. But if you take the universe as a system, you're always going to get it back. Doing that. So this is going to be negative mu k normal force delta x equals. So that's the real difference between saving energy and not saving it. The work done by friction is always a negative, equals to the same terms, but in conservation, the work done by gravity, a conservative force, conserves energy, right? So that's non-conservative, non-conservation of energy, if you will, all that stuff. Understand that? Is that all right?
I have a question about potential energy.
Mm-hmm.
Is potential energy only in the y direction?
Yes, because it's a function of height. Mm-hmm.
Okay, just making sure.
Mm-hmm. More clear on that though. Gravitational potential energy is in the y direction. We're going to see there's another type of potential called spring energy that can be either or, but the spring energy is spring potential energy is a type of potential, but it's all relative to the spring force. And the spring force is also a conservative force that we can put into this equation, and it's also part of the conservation of energy. Up top and down here, we can put it in here too if there's friction. So, good question. All good questions. Everything good questions. Good. So this becomes mu k, normal force. We know if we just flat surface, keeping it simple, that's going to be mg delta x equals terms, right? And like I said, when we get to this elastic energy, we talked about that last time. The elastic spring energy is going to be equal to another type of potential, which is spring potential. So that's another term that can be put in there as well to have a full system. So like if we had a mass on a spring, you know, we have some sort of this is actually an AP problem some years ago. We have a spring compressed, and the question was, you know, something like, what's the spring constant? Because this thing was compressed and here is zero. And then guy got some height h in the air. So what's the spring constant? So what you have to do is identify what's the initial case, the initial situation. What kind of energy exists right here? It's going to all be spring energy. It's not moving, so there's no kinetic energy. Has no height, so it doesn't have. It's not potential energy. So this was the initial, and then this guy was in the air, so this will be final. And so, in the final case, remember at the top, maximum height that it achieves, there is no kinetic energy because the speed is zero, but it has a final height. And therefore, we could figure out what the spring constant is. So different things we'll see. We'll see different examples as we go along, but I just wanted to establish those things for right now. Any questions on the formulas? Conservation of energy. That's the simplest case because you have nothing over here. That all came from the negative delta PE equals delta KE. And then we have friction no longer zero. yeah, so let's do another example. I mean, let's roll through. In your book, you'll see that potential energy is sometimes denoted by the term U. So yeah, trying to think where that originally came from, or the reason for that. But yeah, so you'll see probably go back and forth, but potential energy or this UG, same thing. This is all the gravitational potential energy. So now I'm over in chapter 8. There's really no distinction other than their arbitrary separation, but 7 and 8 are really together. They're all energy. You just start developing things, introducing things in 7 with working kinetic energy and potential, and then we start saving it or not saving it. Let me go to, if you're in your book, let's just scroll. Let's look at chapter 8. I mean, just kind of scroll through it. So tell you some things about it. So we have a non-isolated system, conservation of energy. Basically, they're telling you what kind of energy we're talking about, the conservation of mechanical energy. There's energies of different forms. There's heat, electromagnetic radiation, electrical transmission, but the type of energy we're going to be dealing with is mechanical. So this is just nice to know and need to know down the line, but section 1, nothing really important relative to what we're doing. 8.2, isolated system. We've closed the system off from the environment. We've derived the equation for conservation of energy, and now we're using it. As you can see on page 199, they have the full conservation of energy equation. The I hat and the J hats. Well, you know, the J hat is the y-axis, and so I didn't do all that hat business. I don't think it was necessary, but definitely read through it just for your extra understanding. Nice examples. Page 203, spring-loaded pop gun. We have spring energy that's going to become gravitational energy potential. Section 8.3, totally irrelevant, even for the C people. This is not necessary. Because at the end of the day, in section 8.3, they derive the energy for friction. I think in some other contexts, we could, depends on the approach of any teacher coming at 8.3, just to really pour in the calculus and why, we have the work done by Friction UK mg delta x on that, but not important there. And we go to 8.4, changes in mechanical energy for non-conservative forces. Just threw it at you right there. This is what it is. Threw it at you because we already know what it looks like for conservative forces. So for non-conservative forces, it's this guy right here. So that's all we're going to be working with, conservative or non-conservative. And then now our job is to figure out what's going on in the beginning. What is the beginning case? What's the ending case? Once we establish those, we can do any energy problem, any momentum problem. Because we'll see another conservation principle in chapter 9, talk about the conservation momentum. Same idea. We're going to close the environment off from outside forces and save the momentum in the system. Then power. At the end, we'll get to power. So let's do some examples. They have a difficult time being, in this book, they have a difficult time being introductory, but let's do number 4. If you want,
Mr. Kelly,
yeah.
are we free to go? I have a meeting that started 5 minutes ago.
Oh yeah, well, I thought everybody, okay, yeah, you can take off.
All right, thank you.
All right, see you. So those, let's.
Oh, Mr. Kelly, sorry.
Yeah.
Same here. So there's no skills test this week, and the skills test makeup is Thursday morning at like 8 a.m., right?
The skills test makeup will be after school Thursday.
Okay, cool.
Okay.
I'm gonna go to a club meeting now. Bye. Thank you.
All right. Anybody else can stay, or you guys gotta go? I think with the 2 people gone, I don't want to do any. Maybe I can do a couple of examples if people want to stay back. It's up to you guys. Because what I was going to do is see if you want to do page 218, number 4. You guys there?
We're doing it together, right?
Yeah.
Okay.
Right here. Talk about it. So this is one of the intro ones in the old AP Physics B book. We have a particle of mass m equals 5 kilograms is released from point A and slides on the frictionless track shown in figure P84. Determine the particle speed at points B and C and the net work done by the gravitational force as the particle moves from A to C. All right. So page 218, 4. Yeah, the speed at B and C. Why is there speed at B and C? Anybody know why?
Is it because of the kinetic energy given to them from gravity, but they're falling on the slope, so they move right? And as they move right, it still has enough speed to clear that ramp,
Mm-hmm.
and
Yeah.
then it goes down there, and then it has more speed
Yeah.
as it goes down from B to C.
Mm-hmm. Yeah, because we know at A, if we went from A, let's say that D is the ground, we know that there's going to be a potential energy change from the top. So that all that energy of position at A is going to get steadily converted to kinetic. So even though at B and C, it's not the maximum speed, it's getting there until we get down at max speed. But yeah, perfect. And so now what we can do, with that little bit is we can determine, okay, we can get the speed at B relative to A. So we have 2 points. We have a type of energy at A and a type of energy at B. Then we can find out the speed. And then we can even go from B to C or A to C. It doesn't even matter. You just pick any 2 points and you can find whatever you want. Also, too, in number 4, there are heights at B and C, so it also has potential energy at those points. It doesn't have the maximum potential energy because it's not at the maximum height, but we know that there's some kind of potential energy there. And if B was the ground, there would be no potential energy on the ground. It would be pure kinetic because we're steadily going from all this potential to full kinetic. And the stuff in between are gradations of the two. Right.
I just wanted to make sure.
Mhm.
The only way for a particle or like something with mass, let's say there's two hills and the particle is on the lower hill, right? And there's the other one is higher.
Mhm.
The only way for the one at the lower one to reach the higher one is if it's something from if another thing in the system gave it an extra push to reach the top. Otherwise, it would
Uh,
never reach the top, right?
Absolutely. Correct.
Okay.
Mhm. And that violates our principle of conservation because we're closing off the outside. But yeah, totally.
I think I'm gonna leave.
All right.
Thank you, though.
All right. All right. Anybody want to stay back and do that one? Or you guys had enough? Yes, no. Christian, Leo, Selena, Sin, you guys want to do that one or take off? All right, let's just call it for right now. And we'll get back at it on Thursday. And skills test makeups are after school Thursday.